Hello, everyone. Welcome to another session of ExpoLab Blockchain Speaker Series. Today is my great pleasure to have Alistair Stewart from Web3 Foundation. So a little bit about our speaker today. He kind of have a very slightly different background from one of our recent speakers. So he has a theoretical background. He studied at Oxford and then Edinburgh. And Edinburgh is known to have a strong theoretical computer science as well too. And he was also a postdoc at USC. And in the last few years, kind of shifted his focus into blockchain and in particular, the exciting problem of sharding. And he's kind of been one of the main person behind the sort of the core protocol of Polkadot sharding protocol. So without further ado, please take it away. Thank you.
Hi. So this talk is going to mention a bit about how sharding works in Polkadot, but the overall idea is to discuss slashing in proof-of-stake systems, and in particular, how that applies to sharding. So I want to describe a particular protocol, which is joint work with Jeff and Handan and other people in Web3 research and other people in Parity Technologies who are building this. But yeah, so let's sort of start very generally. So can I switch to the next slide? That's bad. Okay, now there we are. So firstly, I want to talk about permissionless things. We all know why we don't want to trust a central authority. We don't want to be Google or Facebook. And so there's different sort of assumptions you can make when you're dealing with a sort of decentralized system. So we have many actors, and we can make honesty assumptions. Normally, we'd aim to we'd assume that half of people are honest, or 2/3 of people are honest, or something. And for a proof-of-stake system, this is going to be within the system. And so we'd have to assume that some people are honest. And frequently, this would be the assumption we have to make. The other sort of type of assumption is a kind of rationality assumption. So rather than assuming that actors are good, we'd want to assume that they're rational. And then argue that we're going to set up our incentive system in a way that this is going to work. And this is the goal with a permissionless blockchain, right? We want to have some argument that says that it's secure if enough participants are rational. So we can do this by certainly by rewarding participants for correctly participating. And I'm going to particularly be talking about proof of stake blockchain. So in proof of stake, basically, the people who take part in consensus will be people who already have stake. And the sort of end goal of designing the system is to argue that if most stake is sort of in the hands of rational, and indeed, they also need to actually do something and be active. And this is often a problem in practice. Then we argue that the system is going to be secure. Now, one of the interesting things about proof of stake protocols is that while in, say, proof of work, we could only reward participants, in proof of stake, our participants are going to put stake on the line, and that means we can take it away. And so essentially, we have the ability to punish participants as well as rewarding them. And this talk is going to try and examining what the trade-offs are and whether we should do that. So we'd really like to understand our protocols under rationality. Can we do some game theoretic analysis? But this is actually quite hard. So often what we'll assume is only an honesty assumption, like 2/3 of hash power, 2/3 of stake is in the hands of honest people. And honesty assumptions alone are enough to prove these things are correct. For rationality, we can't really do this, but we can try and analyze attacks. So we analyze like selfish mining in Bitcoin or whatever by coming up with games. with the aim of sort of showing that honesty is rational. And it's actually a bit of an open question about whether we can get more in the way of security by. So we have to make honesty assumptions. So can we get more if we make economic assumptions as well? Right, that's part of what we need to ask. So, and certainly there are people that argue that you shouldn't be doing slashing. We shouldn't be doing punishments. And I'm going to try and explain why at least from my understanding of the argument is. So, and now I'm worried. So basically, you're supposed to, right? So we try and design a Byzantine fault tolerant protocol, and basically what that means is if up to say a third or even nearly a half of participants can just do anything whatsoever, and it still works, as long as 1/2 or 2/3 of people are honest. And these particular numbers depend on what your assumptions about the network are. If you can assume everyone has a synchronous connection, then we can get just over 1/2 of honest people is enough to make it work. If you want it to be work, when the network might be bad, when people might not have there's been some time, not necessarily fully asynchronous, but these partial synchrony models, then you need to say that there's more than 2/3 of people are honest. And so the thing is, if we have such a protocol, then maybe we can design it such that if the other guys are dishonest, as long as we have these honest guys, then we shouldn't be suffering a big penalty to performance, and we should be still safe when we have some dishonest people. Right, but on the other hand, if we don't have a third or 2/3 honest, in particular, imagine that more than 1/2 or more than 2/3 of participants are dishonest, and these guys are colluding, then basically they can make any valid chain. They can agree on anything valid, and if we follow the canonical consensus rules, we will agree that this is what the blockchain has decided. Now, one of the annoying things about this is that they can censor the chain, right? So even if we know they're being dishonest, and they're otherwise following the rules, and we know somehow off-chain they're dishonest, there's no point us sending a report to say these guys are dishonest, that they can be slashed, because they'll just censor it, and so they won't be slashed. So we have a situation, particularly in the synchronous case. So if more than 1/3 people are dishonest, they can misbehave, they can do what they want, and we can't slash them. If, on the other hand, more than 1/2 of people are honest, then the bad guys aren't really causing us any problem. So why bother with slashing them? Now, in this sort of asynchronous case, right, asynchronously safe case, if bigger than 1/3 and less than 2/3 are dishonest including, then typically what happens is they can actually just stop us from advancing. Right? If we need a 2/3 threshold to sign off on something to say it's good, and 1/3 of people just don't show up, then they can stop us from deciding anything, which means they don't get slashed either. So then, if they successfully attack the system and they can keep on attacking it, then no one gets slashed. And if they don't have enough people to do that, why would they attack at all? In which case, they don't get slashed. So it is true that slashing incorrect behavior disincentivizes it when there's not a successful attack. But if most of the time we're just slashing incompetent people and not actually dishonest people, then what are we gaining by this? And on the other hand, just having a risk that your tech stake might be taken away is going to disincentivize your participation, right? Because now you need a secure setup. Maybe someone can hack your machine, cause you to do something which loses you money. And it has to be the case that it tends to be coins that blockchain protocols that come from academia, like Algorand, you mentioned we're going to talk next week, Avalanche, Cardano, these so-called professor coins in which people don't slash. And the reason for that is because mostly because they publish papers. They say this protocol is correct if 2/3 of people are honest. They don't analyze rationality, just honesty. And this is what they can prove, that it's correct under honesty. And then you can make the argument that why slash if it just disincentivizes people. And I think this argument actually holds some water for a single consensus system. So here we're sort of talking about a single chain. Now, what's different in when we have many chains? Either because we're in a sharded system or we're talking about interoperating between one chain and another, is that we can report behavior on one chain onto another chain, which means it doesn't even matter if they can censor this one chain. So this is what layer 2 protocols do. If you looked at Plasma and the like, if we have transactions off the main chain, we can use the main chain for disputes. We can escalate to the main chain only when something goes wrong off chain, and sort of try and prove what's going on. And if we sort of force people to lock up tokens before doing this, then we can get an argument that this is going to work. So this is often what we're going to do in sharding when we have this main chain. So basically, you use a main chain to organize who are the consensus participants, like saying that we often want to do that centrally. And the other thing we can do is this thing we're doing with the layer 2 protocols. And so with sharding, we can have one chain we can report to. And also, if we have multiple chains, we can have like bridges between chains. If we want one chain to follow the consensus on the other, we can also report this behavior on the other chain. So now, but we can definitely make sharding work with only honesty assumptions. I'm sure you said you have a system for this. So basically, what you do in the permissionless setting, we'd agree on who our participants are. We'd divide them up into sets, and we randomly assign people to sets of equal size for each shard. And then we maybe do a Byzantine fault tolerant protocol on each shard. Now, this works because, assuming we have a decent percentage honest in the whole system, because if we have enough people, it works. Because if we take a random subset of people, then with high probability, if enough people in the first thing were honest, this thing is honest. So let's get specific. So each shard is going to need more than a third or more than 2/3 honest validators to work. And we assume a bigger bound on the honest validator to the entire system, and we just use Chernoff bounds. So here we are. So Hurting's inequalities, which is simple enough to fit on a slide. And we can push the numbers, right? So there's 1/6 extra guys in the main set that we actually need on any of these shards. And we can push this out to get an equation. And come up with some assumptions. So let's say we have 100 shards. Now in Polkadot, we change validators 4 times a day, or we change keys 4 times a day, or shard assignments 4 times a day. And if we want to be safe for 10 years, then that gets us 365 times 40, 1% chance that any of these chains are going to be attacked, and that gives us a number of validators we need. Of 338.4. It's a big number because we need a lot of validators on each shard, so that we're sure that basically they're all majority honest. Does that make sense?
That makes sense, but just maybe a little bit more insight as to how much this penalty would be, and how do you find the right value of the penalty? And how do you, is
Oh,
that
so
penalty?
there's no penalties in this particular version. Yeah, in this
No, not
so
in
far.
particular version. I'm
Yeah.
just talking about in general.
Yeah.
How do you, I mean, also, is it proportional to the extent of malicious behavior? I mean, that seems to
Right.
be
Yeah.
also
So
interesting.
indeed. So what Ethereum and Polkadot both do is this kind of quadratic thing. So basically, we need a third of people to do something bad to actually cause any damage to the system. So therefore, what you do is when a third of people do something bad, you slash them a very large amount. Or when close to a third of people do something bad, you slash them a very hard amount. But isolated cases, you slash a small amount. You just want to ensure that you just want to slash enough to incentivize people to change their behavior, to increase the security of their validators. Follow better procedures, but not like kick them out of the system completely. There is a danger. It depends kind of how centralized you are. So we ourselves in the Web3 Foundation managed to take sort of 12% of nodes offline, and we got slashed a bit, which was worth all of 2 weeks staking rewards, but probably quite a bit. But that's because, but if you're a small actor and as long as not everyone puts their validators on Amazon, and no one guy controls too much of the system, people don't get slashed too much. There are reasons why we want to slash 100%, and I'm going to get to that. The chief reason why we do that in Polkadot later in this talk. So this is sort of the number we get with only honesty assumption. So as I say, in a sharded system with one of these central chains, now Ethereum 2 have a central chain called the beacon chain, and Polkadot we have a central chain called the relay chain. We can use the central chain to deal with disputes on shards. So if sort of we have one honest validator per shard now, and they can report something to the main chain, then we can slash the guys on the other chain. Now, maybe they could include a short proof that something bad happened, but even if they can't, we can, a single complaint can maybe cause everyone to check, and this would break our scaling, but it wouldn't break our scaling too badly, because it's like either everyone will agree that this block is valid, or whatever it is, or this block is invalid, or something like that. And as long as we can all agree that this is true or false, we can slash someone when a validator complains. And basically that pays for the breaking of scaling. So now if we want just one honest person, the number's a lot better, right? Because now instead of this thing we got from Herfting's inequality for 2/3 of people being honest, we can assume 2/3 honesty for the whole system, and we get like 2/3 to the number of guys per shard being smaller than this probability that we need for this never to go wrong in 10 years across all 100 shards. And that gives us this number of 46.3, which is a lot smaller than the 338. And this is something we get straight away if we can reduce down to one honest person. But there is kind of like, so one thing here is that we know exactly, well, one disadvantage of this sort of system. So there's two big disadvantages. One of them is this so-called availability problem, right? If we have our one honest validator and everyone else is dishonest, they don't need to give this guy the data, right? They can just hold it back and claim it's correct. Now, if you're a Bitcoin and you're a miner and you withhold the actual block, no one else is going to build on it. So there's no danger of an invalid block ever, a block that's gone missing is unavailable, ever being in the longest chain, unless 51% of the miners are dishonest. But the situation is a bit different in a sharded system, because we only need the guys on this one shard to claim it's correct. Then it's sort of, then the whole system believes that this thing is correct, and they don't actually get hold of the data, so maybe it just doesn't exist. There is actually a way to get around this that Ethereum is looking at, Polkadot is using, in which you kind of want to robustify this. So instead of having, like, you want to rely on everyone and not a few people to make these shard blocks available, and we can do that by erasure coding them. So basically we distribute the piece of the shard to everyone, and if we all agree it's available, if we all agree we have our piece, well, okay, 2/3 of us agree we have our piece, at least 1/3 of those are honest. So if we sort of add 3 times redundancy, we can reconstruct from any third of people, and we can get it. So this sort of solves the availability problem or reduces it down to an honesty problem for the whole system. The other problem is that the attacker knows when to mount an attack. So basically, they just wait long enough. They control enough bad guys. They wait for long enough until everyone on the shard is bad, and then they attack. And of course, because there are lots of shards, we only have a few guys on each shard, and the cost, if we're going to slash these guys, is only one in the amount of the amount of shards. So if we have we have 100 shards and every validator is only on one shard, then we slash only 1 in 100th the stake of all the validators when we slash everyone on one shard. Whereas if we sort of have the 2/3 honesty for the whole system, it costs us sort of 1/3 of all staked things to attack the system. And this is much smaller. And so is it actually possible to get more than this, to get an attack bigger than this? Well, not really. So basically, if everyone, if checking validity is atomic, so if we either check a shard block or we don't, and in order to check it, we have to have the entire block. Then we can only check sort of a constant number of blocks. Now, and if this is true, then then we're going to be validating. Then the cost is going to be sort of 1 in S of the stake of the entire system at most. Now, neither of these are necessarily true. So what you could have is you could divide the block into pieces and you could check each individual piece separately. That might change the numbers a bit or change the analysis anyway. The other thing you could do is you could use succinct proofs, zero knowledge succinct proofs. And if you could magically do that, you could have everyone check a proof for every block, and that would get around this point too. So I don't think that dividing into pieces, you still have to ask, you're not going to give these little pieces to everybody, so you're in the same situation. And for the succinct proof thing, it would be really nice if we could do this. I think you'd have to, and the basic problem is that we're really not, we can't really do an Ethereum. We can't really do succinct proofs for Ethereum or something like that. Something, general purpose, Turing complete, that you didn't design specifically to be easy to do in a snark. This isn't practical yet. So, and if we can't, does this work at all? So there's a rather nice blog post that became a paper by Brian Ford and Rainer Bone, arguing that rationality is self-defeating in positionless systems. And they make some very good arguments about basically that we cannot do better than honesty assumptions. And I'm going to concentrate specifically on the one that I don't buy. So you should read the rest if you want to know what they're really on about. And one of the arguments they make basically is this: is that there's more money in the world than there is stake in the system, token in the system, and this means that there can be bigger incentives than we have tokens, and furthermore, the number of tokens in the system or stake or whatever is bigger than the total reward or punishment we can give to an actor who can attack the system. And so at some point there may be enough external costs here for it to be worth it just paying an actor to attack the system, and there's certainly enough money in the world to do this. So all they need to do is to pay to take down the system. They could maybe make up to the amount of stuff in the system up to S by taking down the system, maybe, or at any rate, just steal more money than this maximum reward punishment for the guy capable of attacking the system, and then they'll just do it. So at first sight, this seems kind of foolproof, but really it's not, especially not if we make honesty assumptions. So here's the sort of reason why it's not. So if you think like an expected cost of an attack, there are more things. So even if the cost of an individual attack cannot be made too high, we can still make the expected cost very high. All we need to do is to make sure that most attack attempts are not successful, but are caught. So basically, if most of the time you attempt to attack, we can catch you, slash you, but the attack doesn't succeed, then the expected cost will be much higher than the cost of an attack attempt. So in particular, the cost of an attack attempt to do 1 over S, and we can make the detection probability close to 1, then the success probability only needs to be bigger than sort of 1 in the number of shards, 1 in S here, in order to make this thing the number of stakes in the system. And we can make it higher. You can even make it higher than the total money in the world. It's not, it's just a question of how to make this small. And then one of the nice things is about compared to the formula I had before, is that we don't need to consider how many times the system can be attacked, right? So if you're trying to make the probability of, the system never attacked in 10 years, if we were trying to argue about each time we change the validator set, the probability is really small. Now we can make it 1 in S throughout the entire system. Like we have 1% chance of any attack succeeding, but we catch you all the time, and so it costs you 100 times more than the cost of a single attack. And then basically, you bad guys just don't have enough tokens to attack the system. But one issue here is that we need to make sure that for every attack attempt, the detection probability is actually close to 1. It's not enough to detect successful attacks, or it won't work. So one of the things we definitely need to do here is to use unknown participants. So the problem with the original one honest person design is that we can just wait until there isn't one. So we want to have participants sort of checking that this is correct. So with the availability solved, we sort of want to check about the validity. Are these blocks good? And so we need a way of choosing people. Now we could use sort of system randomness. Normally we think of people self-selecting by, say, using a verifiable random function, which I'm sure Algorand will talk about. So if we sort of have people self-selecting with private randomness, and then they can sort of prove to us that they were supposed to have been chosen, if they actually ever need to report. So we have random people checking who aren't known by the first set of random people who we assigned to the shards, then we can get what we wanted, which is a protocol that works under honesty assumptions, even when a few participants decide. But even if we do something like this, there's still attacks that we're vulnerable to. in particular, this is the difficulty with honesty and nationality assumptions. To assume 2/3 of people honest, this definitely works. If we give too much power to the bad guys, we allow them to corrupt people instantly, even before they know who they are or something like that, which is more or less down to the assumption that every validator is running hack software, where they try and maximize their own thing, and we can just bribe them from another chain. Then nothing is secure. If we're in such a model, sharding just can't work. It's always cheap. But with 2/3 honesty, it does work. And so this is how we do it in Polkadot. So we have a number of guys who we select to back to say initially that this shard block is correct. And we record this on our central chain. We record some kind of header for the shard block along with these claims of correctness. Once that's happened, we distribute these array decoded pieces, and everyone sort of votes, did we get them? And at this point, it's like the backing validators are committed. They can't, anyone can now get hold of this block who wants it, whatever the original guys do. And then we choose guys at random, or they choose themselves, but at random in order to check the shard. They can get it from the major coded pieces, from the original guys, from however, but they can certainly get it. They'll check its validity, broadcast it, and if any of those guys complain, we escalate it to everyone. But if all the guys who said that they were going to check it say it's good, then we believe it's correct. And after some time, we'll finalize and all agree that this has happened forever. Actually, this sort of protocol is a bit optimistic. As soon as we think we know something's available, other shards are going to act on messages sent by this shard. But we're going to delay deciding that this thing is final, that we're never going to be able to go back on it until we're sure it's correct. And so I wanted to argue, like the main theme of this talk, what does this do to the numbers?
So just a quick question on the previous slide. So when do you know, I guess, something becomes available, or I guess it's settled? You said, the protocol, you had like that few steps that you had for Polkadot. So right. At what point you then become certain that something was replicated enough to other, and do they need to send messages back, or do you need to vote?
So in particular, everyone needs to send a signed message saying, we got pieces from the blocks from these shards.
Okay.
So this is everyone sends to everyone, and then everyone sends a message to the main chain, and then it figures out what we have enough people agreeing on. We can probably use some cryptography to get rid of the n squared here. But
okay. So it's an all-to-all communication, because everybody needs to determine that decision, kind of.
Well, it's not quite all-to-all, but it's so the array decoded pieces distribution is someone on this shard so everyone needs to get a message associated with this shard. The number of shards is of course less than the number of people, but it is like a lot of messages. If we're talking of 100 shards and thousands of validators, there are 10,000 array decoded pieces. They're all really small, right?
Sure.
No one gets more than like a constant number of blocks data ever, but yeah, sure. it's an all-to-all.
Sure. So so another question. So that's very interesting. So in terms of kind of a bigger picture, is that within a shard, all the validator need to validate every transaction, but at the global level, still all other shards in a sense are validating an aggregated or an amortized or a batch of transaction for every shard?
Right. So it's not, so to the validators, it's not just the guys on this shard, but also other shards. So actually in Polkadot, validators, right. So one thing I might have had to mention to make sense of this is that we need stateless validation. So we actually separate collation, which is getting these transactions together and creating blocks, from validation, which is checking that the state transition was updated correctly. And we make the latter stateless. So we include like lots of Merkle proofs, like you have to do to a light client to say what the state was beforehand and afterwards, so that the validators don't have to know the state. They don't have to know this many gigabytes of data may be associated with each shard, which means you can check things on any shard without syncing it. This is very important.
I see. Okay, so they don't have the state, but they get enough proof to be able to determine.
Yeah, they have now a bigger block, and they also have this centrally registered what the actual validation function was, what actually is this thing we're supposed to be checking about the shard.
And the intuition there is transferring and computing and validating that proof is simpler than maintaining its state at every shard.
Yes. Well, it's just a lot less data, right? So there's more data with the block, but we don't have to. So the goal is that everyone has the same amount of data as if, within the constant of just doing one chain, even though we have 100 or more chains. So everyone wants to be scalable in terms of their bandwidth, in terms of their computation power, how many blocks they check, and in terms of how much data they have to store.
So kind of, again, taking one step higher in terms of the overall optimization, is that one way of looking at sharding is to distribute the workload. One way of looking at the sharding is to distribute the computation, distribute the validation. But in the Polkadot, the focus is not so much necessarily distribute or divide the computation, is to just ensure the state is really divided, that you're really optimizing the amount of state that each shard needs to maintain. And
so what we're really trying to get is shared security. What we like to do is for one shard to be able to trust every other, and for each of these shards. So in us, our shards are actually different. We call them parachains. They're different from each other. Each chain is sort of different, and really we have lots of chains, and the key idea is that they have shared security, and message passing is easy, right? If we're in one single sharded system, and the key thing is that we all trust the consensus, we all trust the 2/3 validity of the 2/3 honesty of the validators of the whole system. Okay. And then we can trust other chains.
I see.
That's the main goal.
And so is it also the main goal is, in addition to kind of reducing the amount of state that each shard needs to have, is it also
each shard might have a lot of state, but it doesn't have to store anything about other shards. So basically an operator might have, on one shard might follow the shard and the main chain, and they shouldn't have to have any data associated with anything else, but the validators do, but they only have it temporarily. And it's only a constant times more than if they were following one chain.
But the validator is the same validator maybe validating more than one shard as an actual validator?
Right.
I mean, holding the state more than one shard?
So actually, we have this separation, and validators are basically main chain things. They only have main chain state.
I see.
They have main chain state, but they have the stateless, these proof of validity blocks from the shards.
And those proof of validity blocks could still be trusted if everyone that participated in construction of that proof are also faulty?
Yes. So the aim is to so the purpose of validators is to sign off, is to show that these things are correct. The purpose of this protocol is to make sure that these things are correct. We do that by basically having people sign off on this thing and then detecting it with high probability and slashing them, taking away 100% of their stake if they lie.
I see. And what is the path to recovery? So you can identify it, you can slash it, but can you always correct it? Can you always recover? Right.
So what actually we do, so our consensus is so this is where it gets slightly fun. So our consensus is we follow a forkful, a sort of proof of stake version of Nakamoto consensus. Actually, it's similar to the Ouroboros Praus that the Cardano guys came up with. When it comes to creating relay chain blocks. But then we have a second thing called a finality gadget. I don't know if you looked at Ethereum too, called Grandpa, which then later agrees that these things are final. And Grandpa is flexible. We can, it's not tied into the block production and its fork choice rule too much. And in particular, we can hold off on finalizing. So what happens here is that we act on blocks. So as soon as we have these array decoded pieces, we enact the block, it sends messages to the shard block, it sends messages to other shard blocks, and they act on those and so forth. But this is sort of in the stage where we have forks, we can still switch to another check. And then it's only when we have a certain form of people having done these next set of checks, these approval checks, that we will, once we've got all of those done for some relay chain block, for all the shard blocks in a relay chain block, only then can we finalize it. Can we do our Byzantine agreement on it? And this means in this period between, we can roll back, we can switch to a different fork. And that's what we do. So if we catch something in this period, then we just declare this fork, this block invalid retroactively, and we build a fork off its parent.
I see. So this is just to kind of the pre-staging to penalize and so forth, but downstream is where kind of things become finalized.
And our argument is when we finalize the block, the expected cost of finalizing a bad parachain block is expensive. Because most of the time before you finalize it, so one of these approval guys will say, if it was really invalid, one of these approval guys will most of the time say it's invalid, they'll escalate and we'll never finalize it. And we'll roll it back, we'll switch to a different fork without ever finalizing.
I see.
And this is where I was going with all these numbers. So now, like, what's the probability? So we have these sort of these M prime, I called it, guys, secondary checkers. And so out of the 2n/3 honest validators, we assign sort of M prime with them on average. So we do the binomial thing here to do it. And the probability that this is 0, that there's no honest guys, it's about Poisson, and the probability of Poisson of 0, we get e to the -2 M prime over 3 as the probability that none of these guys are honest. And this gives the formula for the expected cost of attack. And we compare this with our sort of 1/s fraction of stake, and this gives us a number. And the number here was of total of both the approval checkers and the back things is about 14. If we have 14 checkers total, then it will cost you more than all the stake in existence in expectation to attack a single shard. This is a lot smaller number than we had even with the one honest. That was 38. With the other one, it was like 300 and something. And so we do this crazy protocol in Polkadot in order to reduce the number of validators per shard down to something sensible. Something much smaller than, say, Ethereum 2 or most of these other systems are attempting. And that just means that we can have more shards, we can have more parachains. Any more questions? All right, we're almost out of time. I did have one more slide that I tried to explain before, but it might not be a good idea to try and explain it, which is whether we could get this approach of committing to something with a certain amount of stake on the line and having a small probability of detection to light clients or bridges. And the answer kind of is yes. So one of the problems we have is that we'd like to convince Ethereum 1 of what's going on in Polkadot. The problem is that for Ethereum 1, we have to basically convince a smart contract what's going on. Storage and computation costs are very expensive. So checking signatures is expensive. it does depend a bit of other cryptography, but even including signatures and public keys is fantastically expensive. Storage costs are fantastically expensive on Ethereum. So we want to absolutely reduce the number you check. And we can do some crazy stuff with succinct proofs, but actually there's a simpler approach. Basically, we claim that a bunch of validators signed something. To do this, we only need to give 1 bit per validator to say who signed it, and we give 1 signature. And what we do is so instead of storing the entire validator set, we just store a Merkle root of all the public keys instead of storing all the public keys. So we can have a Merkle proof of this one public key we need for this 1 signature. And then we wait a bit. In particular, we wait enough to be sure that we can't go back on this first transaction. And then we'd want to have, then basically we just give random validators. We check random signatures of these guys, and we change to, and we accept if all of them signed it. Now, the way you'd make this work is that you'd want people to sign something that was already final, so that they all agreed it was correct. And then we only need to prove that 1 honest person signed it. So we have 2/3 of people signing it. We need to show that 1/3 of them did. So we only need to show that half of the claimed signatures actually exist. And if we ask for m random ones, and the probability 2 to the minus m is the probability that these are all bad. If in fact a third of people, 2/3 of the people signing it didn't sign it, then it's only 2. Then the probability is only 2 to the minus m after checking m things that they could possibly get all these signatures. Now, one problem is we can't get randomness on chain very easily. So on Ethereum 1, how do we do it? Well, the easy thing is to use block hashes. Block hashes actually works. They're biasable because a miner can, the miner sort of some particular block hash could, they could throw their block away and do something else, but this has a cost, an economic cost, which we can also model. And at some point, if we make this number small enough, we can argue about honesty of miners and prove something that works. So we have a proposal to do this and to do these bridges too. So as I say, I think that, and sort of a conclusion is here that because our consensus systems don't exist in isolation, there is a good argument that for a single chain, slashing is a bad idea. In a shard, if you have sharding or interoperability, it makes a lot more sense to slash. And in particular, we think it can allow us to scale quite a lot further than than other systems, and still argue that it's expensive, and then argue under sort of combined economic and honesty assumptions. That's what this talks about.
So let me take this opportunity to, on behalf of ExpoLab and UC Davis, to thank you for this exciting lecture, and thank you so much.